Hello dear students. Today let us learn Reynolds transport formula, fluid mechanics. Let us consider an arbitrary set of material particles of a continuum, that occupies a space of volume V naught at time t equal to 0, and the same continuum after some time, right? After some time when t greater than 0 occupies the space V at t greater than 0. So we have taken a continuum which is moving, right? So initially when time t equal to 0, let the volume be V naught, a part of the volume, arbitrary volume we have taken, and the same volume occupies the space V at time t greater than 0. Remember, our continuum is moving. So we have the material coordinates. We'll call xi naught as the material coordinates and xi as the spatial coordinates or the local coordinates or current coordinates. And dv naught be the volume element in the initial configuration and dv be the volume element in the current configuration as shown in the figure. So we have seen, see, we have taken a continuum here. This is the continuum, some continuum of volume V naught. The continuum is moving. The continuum is moving, and this is at t equal to 0. And after some time, t greater than 0, the same continuum occupies the volume V and the small volume element dV naught in the initial configuration, and in the current configuration, dV is the volume element. Okay, yes. Now, this dV and dV naught are related through the Jacobian. The Jacobian, J as dV is equal to J into dV naught. We'll call it as equation 1. Then multiply a scalar function phi which is related to the motion of the continuum. This is not relation, this is related to the motion of the continuum. And when you multiply phi on both sides, you will get phi dV is equal to phi j dV naught. Now integrating, taking the volume integrals on both sides. On LHS we have dV, so it is integration over the volume V. On RHS we have dV naught, so it is integration over V naught. Okay. Now taking the material derivative on both sides, so capital D by dt on LHS and capital D by dt on RHS. Now concentrate on the RHS. So this integral and the derivative can be interchanged. So integral over V naught outside, okay, d by dt inside of the same thing, phi j dV naught. Now d by dt of, three functions, phi j dV naught. So we can use product rule here. We'll take phi and j as one function and dV naught as the other function. Phi j as one function and dV naught as the other function. Let us, differentiate using product rule. The next step. So this is our next step. We can see here that is equal to integral V naught as it is. So what is changing here is, see, d by dt, differentiation of the first function, the second dV naught as it is, plus the first function as it is phi j and differential of dV naught, the second function. dV naught, the second function. Okay. What is our V naught? V naught is the volume, initial volume. To start with, volume V naught is constant, is fixed. So dV naught is also fixed, right? So capital D by D naught of any constant is 0. So that is why this part is 0. This whole, this term, there will be no contribution by this term. Now what is remaining? Remaining is this whole thing, right? And we have, two functions here. We have two functions here, phi and j. Phi and j. So differentiation of these, we have to use again product rule. Okay. So again using product rule, our LHS is same and the product rule on the RHS. So dV integral V naught as it is. Differential of the first function, j as it is, dV naught as it is, right, plus phi as it is and differential of j. And dV naught, of course, in both the terms, dV naught remains the same. Okay, now what is dj by dt? By Euler's formula, we have dj by dt is equal to j into divergence of the velocity. So using this Euler's formula, just substitute in the next step. So what is the next step now? That is equal to, see, in the place of dj by dt, we have put this j into dv, divergence of the velocity, by using Euler's formula. Okay, now in the next step, what is capital D by dt? Capital D by dt is nothing but the material rate of change, and we know that the material rate, time rate, is related to local time rate like this. So dou phi by dou t plus v dot del phi, the relation between the material time rate and the local time rate. Okay, so d phi, capital D phi by dt is dou phi by dou t plus v dot gradient phi j dv naught as it is, and the remaining phi also as it is, and divergence v is nothing but del dot v. Divergence of v is nothing but symbolically it is del dot v. Okay, then connect these two. So v dot del phi plus phi divergence v, we have an identity that is equal to this part. That is equal to this. So we got the LHS. What is our LHS? LHS is the material time rate of, okay, the volume integral phi dv is equal to the material. Now watch, we had dv naught here, and so we had v naught, integral over v naught, right? Now j dv naught is nothing but dv. So we should have the corresponding integral also as v. Fine. Okay, so this is the LHS equal to integral over the volume v, the local time rate of change of phi, and del dot phi v, or divergence of phi v, that is on the RHS. Fine. So this is called Reynolds transport formula. This happens for any scalar function phi related to that continuum, or related to the motion of the continuum. Okay. Now this volume integral is for the both the terms, for the first term and also for the second term. Now if you take the volume integral for the second term, you have volume integral of divergence of phi v, right? So by using Gauss divergence formula, see that volume integral is converted into surface integral phi v dot n ds. Phi v dot n ds. Fine. This is also another form of Reynolds transport formula. And this equation, or the Reynolds formula, indicates what? Indicates the rate of, what rate? The material time rate of, change of the integral of phi over a material volume v is made up of two parts. Number one, the integral of the local time rate of phi, that is the first term, we are talking about the first term on the RHS, over the volume v, and the second term indicates the flux. Whenever we have a surface integral, right, some vector dot n, whenever we have any vector dot n, that indicates the flux of that vector across the surface S enclosing the volume V. Okay, so here in the place of the vector we have phi into V, right? So the flux of phi V across the surface S enclosing the volume V. This is in words, Reynolds transport formula in words. Okay, if that phi, if by any chance happens to be equal to 1, then the phi is 1, then capital D by dt of the volume integral, the integrand is 1 here. 1 into dv is dv equal to, so phi is 1, so no dou phi by dou t will become 0. So phi is 1, so second part of the second term on the RHS, v dot n ds. And this is the Reynolds transport formula, and very, very important whenever we have the continuum, moving continuum. Whenever we have the moving continuum. Okay, guys. So let's stop now. We shall meet again later.